Today we are going to use DFT to calculate the Peierls transition in a system. And for the purpose of simplicity, I consider a simple case, which is a hydrogen chain. The Peierls transition says that the uniformly distributed hydrogen chain system is unstable. So it will spontaneously lower its energy by the dimerization. And so which means that the x1 will be different from x2. And in order to quantify the dimerization, I define a quantity d, which measures the difference between x1 and x2. I'm going to use the ABINIT program for the calculation, and here is the input file for the ABINIT program. So I'm going to use the Fermi-Dirac distribution smearing for the calculation by setting OCC OPT equals to 3. The reason is that for the non-dimerized system, it's a metallic system. So that's why we need to have some smearing temperature and the fractional occupation numbers to characterize this metallic system. And so the smearing temperature I'm going to use is 0.05 electrovolts. And the E-cut I said is 800 EV. And I'm using 5 bands for the calculation, which means that I also plot some unoccupied constant bands in the calculations as well. I use the PBE exchange correlation functional for the calculation. And I also print out the density in order to make this plot by setting print den equals 1. For the key point sampling, because this system is only periodic in one dimension, so I set 20 key points in that dimension and set 1 and 1 in the other 2 dimensions. And I do not shift the key points, so that's why I put n shift k equal to 1, but let the shifting to be 0, 0, 0. So which means that we're going to have a gamma-centered key point mesh without any shifting. So here is a definition of the cell. And so it's a one-dimensional system. So which means that we have a large unit cell in the y and the z directions. In the x direction, it's 2 angstrom. This is because I set the a parameter equal to 1 angstrom for this system. So that's why the cell length in the x direction will be 2 angstrom from here to here. And in other words, we have 2 hydrogen atoms in one unit cell. The position of the hydrogen atoms are given here, and ABINIT provides a very convenient way to scan this d value. So we're going to do 10 different energy simulations for 10 different d values. And the initial d values is 0. So that's 0, 1, 5, 5, 5, 5. So after that, we gradually move the position of the second hydrogen atom in the system. So that's why we add 0.05 angstrom to the second hydrogen atom in my system. So that's why I put 0.05 to x angstrom plus. And after running this program, you will get the energies for all the d values. And so here I put them in this table. It will be easier if we plot them to show the graph. So we see that, so this is a graph for the energy versus D, and we see that your energy will go lower if your D goes larger, which means that the system will spontaneously decrease its energy through the dimerization. However, at some point of time, if you keep increasing the d values, your energy will increase. And this is because if you keep increasing your d value, and these two hydrogen atoms, they are going to get very close. So that's why the energy will increase. Here, I also show you a MATLAB script. Try to fit the lowest 3 points, which is here, 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 with a parabola. And in order to find the minimum energy along this line, and also the minimum energy position, which is the smallest d value for this position. You can see that I just give the energies for these 3 points, this one, and this one, to here. And I also gave the d values, this one, 0 0.1, 0 0.125, 0 0.15, to here, and here. I use a polyfit function in MATLAB and to fit these 3 points with a parabola, and then I compute the lowest position for this parabola. In order to quantify how much energy is lowered during the dimerization, we can define the energy gain by calculating the difference between the energy here at d equals to 0 and energy here d equals to d minimum. So the energy I got is this value per atom. Okay. It's also very important to note that actually different levels of functionals will give you different d values, d minimum values, and the E gain. In order to demonstrate that the energy gain and the d minimum also depends on the exchange correlation energy functional you used in your simulation, I also performed the simulation with a Purdue 192 LDA functional by simply changing IXC equals to 7 in the ABINIT input file. And you can see here, so the blue line is the PBE that we obtained in the past, and the orange line is the LDA we obtained now. You can see that your D minimum value is become smaller, and also your energy gain becomes smaller as well. So I summarize the results here, and which shows you that your energy gain actually is pretty sensitive to the functional that you use in your calculation. And some authors in the literatures, they also try to use the hybrid functional for calculating the energy gain and the d value, and the results are also very different from the PBE and LDA. So that's why the cautions should be paid in practice if you really want to study the Peierls transition of some system, because the dimerization and energy gain is sensitive to the exchange correlation functional you use in your calculation. And maybe for many cases, the hybrid functional like a B3-lib will be your best choice. But of course, if your unit cell is large and the hybrid functional is expensive to use. But just keep in mind that if you can afford doing hybrid functional calculations, and you can try that, and to verify that if the results really depends sensitively on the choice of the functional. So here I'm going to show you the variation or the change of the band structure upon the dimerization. I just try to extract the eigenvalues for all the bands from my calculation. And so I only consider these key points due to the symmetry. So the negative key points are not considered in my table because of the symmetry. I have 5 bands in my calculation, so the eigenvalues are listed here. So here I'm just going to show you that how to extract the eigenvalues for these 5 bands from the ABINIT output. So here is the output file from ABINIT. You can see that I'm doing 10 different data sets by scanning the D values. And the D minimum position is close to the data set number 6, which means that I'm just searching for the data set number 6 in this output file. Okay, so this is the results for the data set number 6. And you can see the self-consistent calculation of Kongshamn DFT here. At the end, ABINIT is going to print out the eigenvalues for all the key points for all the bands. And here you can see that this is key point number 1. We have 5 bands, and the weight for the bands is 0.05, and the fractional coordinates for the key point is here. And so the eigenvalues from lowest to the highest bands are here, 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 here for this key point. And this is the starting point of the second key point. The weight for this key point is 0.1. You have 5 bands for this key point as well. The fractional coordinates for this key point is 0.0500. And the eigenvalues for these 5 bands at this key point is this number, this one, and this one. So those are the eigenvalues I'm going to extract it to my table for making the band structure plots. Okay, so now welcome back. And so first I plot the band structure for this undistorted case. The plot is shown here. And the picture for this hydrogen chain looks like this. So it's an evenly distributed hydrogen chain. It's undistorted. You can see that you have a 0 band gap, which is because your lowest band meets the second lowest band at the boundary of the first Brillouin zone, which is at k equals to 0.5. So which means that this origin band and this blue band, the occupation number are both 1 at this point. So that's why this is a metallic case. And this also explains why we use the Fermi-Dirac distribution in our calculation for this system. I also made the band structure plot for this dimerized case, corresponding to D equal to 0.125 angstrom. And the picture for the hydrogen chain looks like this. You can see a clear band gap opening here. And this blue band is always doubly occupied for any key points here. So that's why this is an insulating system. And hopefully that this tutorial can help you to perform Peierls transition calculations with DFT. And thank you for watching. See you next time. Bye-bye.